Hello everyone, my name is Yuan. In this video, I'm gonna introduce the project that I'm working on, optimal design of blank configurations. The project is continuing the optimization of my senior design project I did last semester, cooperated with Van Voorst Lumber Company. The basic product from the company are wooden rails of different sizes for commercial applications. The focus of my design is optimization for the two ends of the wooden rails to reduce production cost. The two ends of wooden rails are circular flanges that are cut from blank, made from various combinations of lumbers. So, the most complicated part of creating the production plan is to design the configurations of blanks to minimize cost of materials. In the senior design project, our team did a linear programming optimization in C++ and Excel for the problem based on the real-time inventory of lumbers and orders of wooden rails with different sizes that demonstrate around 4 to 5% decrease in material costs as compared to company's previous algorithm. We built 25 different potential qualified blank configurations for each size of flanges and made the production plan by making choices among the existing configuration designs. While optimized a lot, it still left space for further optimization because biased design based on the specific orders and inventory may not be included in the 25 given choices. So, in this project, I hope to use a nonlinear optimization to go a step further for the project, which is my motivation. I'll design new blank configurations specifically based on the inventory and orders. The design for each potential sizes of flanges follows Pythagorean theorem as the figure shows. The construction is started with the center board and is built board by board until all dimensional requirements are satisfied. Set C, for instance, represents the radius of a given flange plus a 1-inch buffer. This 1-inch buffer is added in case of error by the chainsaw when the flange is cut out of it. Set B represents half of the length of the next board's minimum length required to assemble the blank. Also, for safety reasons, we should make sure that after the flange is cut from the blank, the width from the tangent line that is parallel with the boards to the connection line for the first board from outside should be greater than or equal to 4 inches. Now let's talk about the mathematical model I built for the project. In my project, I'm going to consider to produce two kinds of blanks that are blanks for flanges with 100-inch diameter and 50-inch diameter. In the model, x equals to 1 represents the blank for 100 inches. X equals to 2 represents the blank for 50 inches. K represents the location of the boards when building the blanks. K equals to 0 represents the location of center board. There are at most 19 boards used in a blank. To build the blank, we can choose lumbers with widths of 6 inches or 8 inches and lengths of 108 inches, 96 inches, 84 inches, 72 inches, 60 inches, 54 inches, 48 inches, 42 inches, 36 inches, 30 inches, and 24 inches. dx represents the diameter of flange x. So here D1 equals to 100 inches and D2 equals to 50 inches. PLW represent price of lumber of width W and length L. And ILW represent inventory of lumbers of width W and length L. MX is the amount of flange X that the company is supposed to produce. There are three variables in the model. YSK is the variable represent if location K in the blank for flange X is used. ZLW represent number of lumbers of length L and width W that will be used to build the blanks. CLWXK represent if we are gonna use the board with length L and width W to build board K in the blank of flange X. Our basic objective is to minimize total cost of materials, which can be represented as summation of price of lumber times number of lumber that will be used. There are 5 constraints in total within the model. The first one is we should make sure the lumber inventory should not be exceeded. The second one is ensure enough blanks should be built to satisfy the others. Our third constraint is sum of board width should match flange diameter. The fourth one is according to Pythagorean theorem, the square of the required length of the board over 2 plus the square of the distance from center to the end of last board should be greater than or equal to the square of the radius. Well, the last one is for the 4-inch requirement we've mentioned before, that after the flange is cut from the blank, the width from the tangent line that is parallel with the boards to the connection line for the first board from outside should be greater than or equal to 4 inches for safety reasons. Based on such a complex mathematical model, I'm going to optimize the problem through the rest of this semester. Some acknowledgements here. The project is based on the senior design project I did last semester, so I want to specific thanks to my senior design team member Sehil, Edward, and Jacob, and our advisor Professor Jugogarg. Also, thanks Grant and Mike from Van Vers Lumber Company for providing tremendous guidance last semester. Alright, thank you very much for your listening. If you have any questions, please contact me by email.